All right, everybody, welcome to Earth Science. Earth's Guts. Part of this unit, a big part of it is concentrating on what's going on near the surface, but a big part of this unit is also what's going on throughout the whole entire interior of the planets. And how do we know what's going on down there? There's always like sci-fi, people bring in sci-fi movies and say, oh, there was this one where they had this like spaceship thing and it had a drill on the front and they went down through all the layers. Not going to happen. Incredibles, not going to happen if you saw The Incredibles. Or Incredibles 2, I don't remember. So how far have we actually, truthfully, and within the limits of our capabilities, really drilled down into there? And you just watched a video on this. This is just to like get it down. That the Soviet Union tried for decades to dig the deepest hole and still stands, making it about, I'm going to put it over here first, 12,262 meters down. Now, the Earth's radius, we're going to find in kilometers, is 12,756. But we need half that, right? 12,756 over 2 to give us a radius of 6378. So Earth's radius is 6378 kilometers. I guess kilometers are already written there. I'll do it. So this in kilometers, this number in kilometers, I don't know if you remember doing this. You just go with the decimal, slide it on down. That's why the metric system's nice and easy. 12.62, let's call it 12.3 kilometers. All right, run a percentage then. Percentage-wise, how far did we make it from the surface down to the very center of the Earth? If you want to drill down and hit the center of the planet. Kilometers over 6,378 kilometers. And since it's a percentage, we do times 100. Our buddy there in the last video forgot the step. It happens. 12.3 over 6,378. That scary low number, and then to do that as a percentage times 100. Meaning, all of that 0.19, let's go 0.2. And that's where he made an error. He didn't do the multiplying times 100. 0.2%. So decades and decades and decades of work, and we made it 0.2% into the planets. So how do I have the audacity to stand in front of you and say that here's what the inside of the Earth looks like, here's its properties, here's temperatures and pressures and compositions and all of this jazz. It's taken a lot of work, but it's not direct observation. We've had to infer it. We have not directly observed much of Earth's interior. How do we know what's going on down there? Is by looking at waves that pass through it. Now, I always use the kind of the corollary of an X-ray. You know, I hurt my knee once. I had to go get an X-ray. How does that work? They put my leg in between some radioactivity and a film, right? A radioactive source that passes through my leg, but it bends and bounces and absorbs differently in muscle than it does in bone, and differently than it does in skin. So that way, when it comes out the other side, that pattern is different than when it came out of the radioactive source. It hits the film, and then they can look and they can see my bones, right? I've never directly observed one of my bones. People tell me I think it's 206. My biology teacher tells me there's 206 bones in there. I've never seen one. Like, what are you telling me? How do you know that, right? You've never observed it. But, in the same sense, we've never observed the inside of this planet. But we've done the same trick, the X-ray trick. Only instead of doing it with actual X-rays, we can do it with seismic waves, earthquake waves, shock waves that come out when an earthquake takes place. If we can detect these waves, we can see how they refract, which is a term we've had before. Hopefully that clicks with you. It's when a wave bends because of entering different densities. Sometimes they also reflect, sometimes they absorb. And by seeing where an earthquake takes place, and they're happening all over the place every day, and seeing what happens to those waves, we've been able to pretty much line up like, okay, this must be a different layer here, made of different stuff. And then if the earthquake, another earthquake, the same day or another day goes off over here, and it gets sensed in the same pattern every time. This is just an arbitrary space. Any earthquake that takes place on the planet, here's how the waves travel, and note that they interact differently with these different layers. That's allowed us to figure out what's going on down there and to delineate those, just like an X-ray, just like they looked at my knee to say that it was fine that day. But that's how, it's using that idea of waves traveling through to infer something that we can't directly see. So if the Earth were a uniform material and a uniform density, like a lacrosse ball, it wouldn't bend at all. They would just go in straight lines. But they do. They bend all over the place. All right. Now we haven't done, and we're not going to today, this idea of P wave and S wave. We're going to do that soon. But for now, let's just say they exist. There's a thing called a P wave that earthquakes release. There's also a thing called an S wave that earthquakes release. And you can see as they travel through, they do different things. And we'll have to get into all of this. Hey, these ones don't go through the outer core. That tells us something. We'll have to think about that. Hey, these ones do, but they bend pretty severely, and there's none received over here. So all of this has allowed us to say, hey, as New York State, we can publish this reference table, and we're pretty sure we're not lying about it. Look what it says. Inferred properties. We have inferred what goes on down there. All right, so that'll be good for today. We'll catch you guys soon.